Am I audible? Okay, thank you. Thank you, Mohan. Thank you, Vargi. Uh, we would be continuing with the discussion on exergy, and the plan is to derive one very interesting expression uh, for an exergy of a closed system. But before that, I'm just testing your understanding. And as a way of that, I have designed few poll questions, of which you are attempting the first one. So let me close the poll one and share with you the results. So about 80% of the students have voted so far. So the question which was asked in the poll is about what happens to the exergy when the heat is transferred through a finite temperature difference. Okay, and we have discussed this n number of times that when we are talking about the heat transfer through a finite temperature difference, it is an irreversible heat transfer. And whenever there is an irreversible process happening, okay, that leads to the exergy loss or exergy destruction. Or in other words, there is a decrease in available energy whenever there is an irreversible heat transfer, when the heat transfer is through finite temperature difference. Okay, so about 50% of the class has understood this. I'm sharing the results with you. So you see that the correct answer is decreases. Okay, that is the correct answer. So about 50% of the students have understood this concept. Okay. So those who have not understood this, as I keep on saying, you need to visit the videos which have been shared with you so that you get to hear it again and again and see that your concepts are clear. Okay. Let me run the second question. I'm hiding this first one and I'm running the second question. This is again with reference to the discussion which we had. Okay. The question is about your understanding of the data set. We have been discussing that in Exergy calculations, we assume Uh, so we have been discussing the concept of dead state when we talked about exergy. Dead state means the system is in equilibrium with the surrounding. Okay, and basically, as you know, that exergy or available energy is nothing but estimation of the maximum work potential. Okay, so to realize this maximum work potential, the system has to reach its minimum. Okay, and what is that minimum or the lowest point? The system has to reach the environment. Okay, means it has to reach to a state which is the state of the environment. So in Exergy, we define a concept called as dead state, meaning that once the system reaches this state, which is called as a dead state, it is no longer possible, whatever you do, it is no longer possible to extract work out of the system. Okay, so we say that the system is now dead. Okay, in a way, the work potential is exhausted. And why is that happened? That has happened because there is now the system is now in a thermodynamic equilibrium with the surroundings. So the correct answer. So let me close this poll and let me share the result. I'm closing this poll and sharing the result. So the correct answer is the dead state is the state where both, that is, the correct answer is all of the above. The system gets into thermodynamic equilibrium with the surroundings, and because of that, because the system has now is into a thermodynamic equilibrium with the surroundings, the work potential is exhausted. Okay, so no longer one can extract work from the system. Okay, so that is the meaning of dead state. I hope that is clear to you. Mohan, poll दिसत नाही का? Okay, let me see what you are viewing. दिसतोय ना रे? Okay. So as you see on the screen, the correct answer is all of the above. Okay, and about more than 50% of the students have correctly answered this. Okay, let me go to the third question. I'm hiding this poll and I'm going to the third question now. So this has to do with your understanding of the quality of energy, namely heat and work. Okay, so this is in a way going to test your understanding of quality of energy. So as I see that majority of the students are getting this wrong. Okay. You need to appreciate that what is this contribution of second law of thermodynamics? The contribution of second law of thermodynamics is that it tells you that the entire amount of heat cannot be converted to work. Okay. And in a way, it tells you that the heat is a lower grade energy and work is a high grade energy. Okay. So one can convert the entire amount of work to heat. There is no thermodynamic limit to it. But one cannot convert the entire amount of heat to work. Okay, that is the contribution of second law of thermodynamics. Now, why can we convert the entire amount of work to heat? That is because work is a high grade energy and there is no there is no entropy transfer associated with the work transfer. We have discussed this n number of times that whenever there is a heat transfer, there is a entropy transfer along with the heat transfer. Okay, so along with the heat flows the entropy, but along with the work, there is no flow of entropy, right? And because there is no flow of entropy along with the work transfer, it follows that the exergy of the work transfer is equal to the energy of the work transfer. Okay, so energy work, which is a form of energy, is equal to the exergy when you are talking about work. But when you are talking about heat, okay, then the energy is greater than the exergy, because exergy is a high grade of is basically talking about the work potential. Okay, so always the heat would be greater than exergy, or in other words, exergy would be less than the heat transfer. But when you are talking about work transfer, the exergy value of work transfer is equal to the uh, uh, energy value of the work transfer. Okay, this you need to keep in mind. So the correct answer is, let me close this poll. About 60% of the students are voted, and I already answered it, so there is no point of running this poll again. So just sharing the results with you. Okay, and as you see on the screen, what is seen is that the correct answer is the option A, which is 40%. Okay, so 40% of the students have answered it correctly. That the exergy of the work transfer is equal to the work transfer. Okay, it is neither more nor less. Okay, why is that so? Because along with the work, there is no flow of disorder. There is no flow of the disorderly state. Right? There is no flow of entropy. I hope this is clear to you. Let me hide this and go to the poll question, which would initiate the derivation, which I am planning to take today. Okay, so my derivation is about this, a piston cylinder arrangement. Okay, and I'm asking you this question, which is a very obvious question. I hope most of you would be answering it correctly. That is my belief. I'm talking about the piston cylinder arrangement without walls. Okay, and I'm asking you whether it is an open system, isolated system, or a closed system. Okay. You need to vote fast. Only 30% of the students have voted so far, and because the point I'm going to discuss is the calculation of exergy considering an piston cylinder arrangement without walls. Okay, with the gas enclosed. So I'm going to derive an expression. Hopefully you had watched the video which was shared by Professor Burupkar. Okay, and if you have watched it, it will be easy for you to comprehend this, because I'm going to uh, use the same method for deriving the expression. Okay. So let me close this poll. About 50% of the students have voted. Okay, and I'm closing this poll now. The question is the piston cylinder arrangement. I had asked whether the piston cylinder arrangement without walls, whether it can be assumed to be an open system or isolated system or a closed system. Okay, as is a pattern generally, what I find is that about 50% of the class is good in understanding. The other 50% is struggling to understand the concepts. Okay, so here also of the students who have voted, about 50%, of the students have answered the question correctly. Okay, so I'm closing this poll and I'm sharing the results with you. Okay, so allow me to close this poll and share the results. So the poll is closed now and I'm sharing the result. Okay, so 48% of the students who have answered that it is a closed system, they are right. Okay, those who have said that it is open system, it is wrong. Others who have said it is isolated system, it is also wrong. Okay, it would have been an isolated system had the piston cylinder arrangement. Uh, See, when you are talking about an isolated system, we are talking about no interaction. Okay, no energy interaction between the system and the surrounding. Okay, in the closed system, there is a possibility of energy interaction, right? And hence, this is the correct answer is the closed system. Okay, so I'm hiding this. And should I take the last question? Okay. A related question, and then I would start the derivation. Okay. So I'm launching this final question. Okay. Think over this. Okay. We are talking about a closed system now. So you can imagine a piston cylinder arrangement in front of you. Okay. And answer the question. So the options are, if there is a closed system, uh, the work transfer is zero. That is the first option. Second option is work transfer is a boundary work. The third option is both the heat transfer and work transfer are zero. And the last option is the work associated with flow system is always the flow work. Okay. So as I see, a very small number of students have attempted this poll, and of them also very few students have answered this correctly. Okay. Very few students. So I will be spending one more time. I want all of you to vote, okay, because this understanding is very important if you want to understand the derivation, okay, which would be followed. I will be discussing this derivation after this poll. So please vote fast. Okay, I'm closing this poll and I will be sharing the correct answer. So let me close this poll. Let me share the result. The correct answer is option 2. That is, the work transfer is the boundary work. Okay, because it is a closed system. And if it was an open system, the work transfer would have been the flow work, right? We'll discuss this again, but please note that the correct answer is the closed system interacts with the surrounding, okay, by heat transfer and work transfer, of which the work transfer is the boundary work, okay, and not the flow work. So that is not the correct answer. So I'm hiding this, and I would be now sharing my board, whiteboard. Okay, I will just spend some time in that. Let me try to share this. Okay. Let me wait for this. Okay. So as you, so yeah. So the whiteboard is now in front of you, and I will be starting with the derivation. Okay. I will be starting with the derivation. Okay. Sorry, just a minute. I messed up something. Yeah. So let us start with the derivation. I am going to talk about a closed system. I am going to talk about a closed system. Okay. And the objective is to derive an expression for the Exergy closed system, Exergy, or also known as available energy. So that is the objective. Okay. So I have a very small derivation, but an interesting one, wherein I would be deriving an expression for Exergy or available energy of a closed system. Okay. And as I said, a closed system can be taken as something of this form, where there is a piston cylinder arrangement and there is some gas in it. Okay. And this is this system. Okay. This system is at certain state. Let us say that the state is some pressure is P1, the volume is V1, and the temperature is T1. Okay. So this is the thermodynamic state of the closed system. Thermodynamic state of closed system. Okay. You are aware of what is the thermodynamic state. Okay. So this is the thermodynamic state of a closed system. And let us assume that the dead state is defined as P naught, okay, and T naught. Okay, T naught. These are the parameters of dead state, which means that which you can assume that the pressure is the atmospheric pressure P naught and the temperature is the atmospheric temperature T naught. Okay, this is the dead state, right? Now this is a closed system and we are interested in calculating the available energy of this closed system. Meaning what? Meaning we are interested in estimating what is the maximum work potential. What is the maximum work potential of this closed system, right? Now, the closed system, as I said, the closed system can interact with the surrounding by two ways. Closed system can interact with the surroundings by two methods. And what is that? Interact either by heat transfer, let us say that some heat transfer Q, and this closed system can interact with the surrounding via the work transfer, and this work transfer for a closed system is the boundary work, meaning the boundary moves. Okay, this is the boundary work. The boundary moves. Okay, so this system is now, this system has certain internal energy, and we are interested now. This system has an internal energy, right? Because it is at a certain state, P1, V1, T1. So this system is having certain internal energy with it. Now this internal energy of the closed system, how much of this internal energy is available, is the available energy? That is our question. Okay, that is our question that we are going to derive, right? So how much of this is available? Now, as I said, that this closed system, because it is at a higher temperature T1, let us say that this T1 is greater than T0. Okay, and if this is so, then you know that because this T1 is greater than T0, so there is a temperature difference which would lead to the heat transfer Q, from the system, from the closed system to the surrounding, surroundings. Okay, to the surroundings. So this Q, which is at a temperature T1, is associated with certain exergy. This Q is associated with certain exergy, which you would be finding out, right? The second thing is that you find that this pressure P1 is greater than P0. Okay, the pressure P1 is greater than P0, and because this is a piston cylinder arrangement, you can imagine that because this pressure P1 is greater than P0, that would lead to the boundary work. So that is, in other words, this piston would move. Away from the dead center, right? And the gas would expand. Right? So this is the boundary work which can be done. Now this boundary work is done with the surrounding being at pressure P0. Okay, so there is something which is called as a useful work. Okay, there's something called as useful work. So let me go to the next screen, or let me write it. Okay, I've gone to the next screen, and let me talk about what is a useful work. So as I said, the piston is at a certain pressure P1, it is at a volume V1 and temperature T1, whereas the dead state is P0 and the temperature is T0. Okay, so this work, the boundary work would be actually the PV work. Okay, it is the, suppose, let us say that there is some expansion, and this expansion is infinitesimally small expansion, okay, dV. Okay, so then this boundary work dWb will be equal to P1 into dV. Okay, PdV. This is a PdV work. Okay, now there is something called as, you need to understand that there is something called as useful boundary work. Okay, and what is that useful boundary work? That useful boundary work, you need to understand, is the work which you are actually going to get. Now, what is the work we will be getting is this work which you are getting as a boundary work would be less than the it would be more than the useful boundary work. In other words, we need to account for the resistance which has been provided. Okay, so the useful boundary work, or the net work, in other words, the useful boundary work with the subscript BU, it would be, I'm talking about infinitesimal change, so it would be the boundary work minus the resistance, okay, the work, okay, used for overcoming the resistance. Okay, so this is the work which is the negative work used used up for overcoming the ambient resistance. Okay, overcoming the resistance from the surroundings. Resistance from the surroundings. Okay, this you need to understand, right? So this is the useful boundary work, right? Now, so as I said that this system interacts with the surrounding, okay, by two ways. One is through the boundary work, and other is through the heat transfer. So let me talk about the infinitesimal heat transfer del Q. Okay, let us say that there is an infinitesimal heat transfer del Q. Now, and why is that so? That is because of the temperature difference, T1 and T0. Now we need to calculate what is the exergy because of this, or what is the available energy because of this, and we need to calculate what is the exergy because of this. What is the exergy value because of this? Okay, and once you calculate this, we need to calculate the exergy total. So we need to calculate exergy total. So exergy total would be the exergy. Now, how do you calculate the exergy of the heat? So for calculating the exergy of the heat, we need to assume a hypothetical engine, a Carnot engine, which should operate between this temperature T1 and temperature T0, and this Carnot engine would reject certain heat del Q naught, and this work of this Carnot engine, let us say del WC, this would be this del WC, which is the maximum work potential of this heat, is the exergy associated with the heat transfer del Q. Okay, so it follows that if you want to find the uh, exergy or dW total during this infinitesimal very small dV and a small del Q heat transfer, and we need to get the sum of this. What sum we need to take? Del WC plus del W boundary work, which is useful work, Okay, so let us call this as some expression 1. Okay, are getting this? So for calculating the exergy, we are considering a small transfer of it del Q. Okay, and we are considering expansion dV. What we are doing is that during this small expansion dV, we are calculating the boundary work. Okay, useful boundary work, not boundary work, useful boundary work as the boundary work minus P naught dV, which is the work used up for overcoming the resistance from the surrounding, or net work. Okay, net boundary work or useful boundary work, and we are adding this to the exergy of this heat, and the exergy of the heat we are already seen can be calculated by assuming this heat to go to a Carnot engine, and it rejects the heat del Q naught. Okay, the work output of this Carnot engine is the exergy. Okay, so let us start doing this. So I am drawing this. Let me calculate now the exergy because of the heat transfer. So P1, V1, P1. So exergy, as I said, because of the heat transfer, when you are talking about del Q, okay, exergy of this del Q when the dead state temperature is T naught is calculated by assuming that this heat is flowing to a Carnot engine, a reversible engine. Okay, Carnot engine, and this reversible or Carnot engine, that calls as Carnot engine or reversible engine. This work which the Carnot engine gives, okay, that is the exergy of this. Okay, and what is this? This is equal to what? Del WC. This is the exergy of the heat transfer del Q. And what is this from the energy balance? This del Q is del W is del Q minus del Q naught from the first law of thermodynamics. From the first law of thermodynamics, right? Energy balance means energy balance, right? So the exergy associated with the small del Q would be del WC, which is del Q minus del Q naught. Now, if you apply the second law to this, it is del Q by T, that is in this case T1, is equal to del Q naught by T naught, and I would put a negative sign here because the heat is rejected. Okay. So what you get is del Q naught is equal to minus T naught into minus del Q by T. I hope you are writing down this derivation, right? Del Q by T1. Okay. So this is what del Q by T1. So when you substitute this over here, so exergy del Q is equal to that is the work output of the Carnot engine, which is del Q minus T naught into minus del Q upon T1. Now you might ask me why I have taken a negative sign, because actually I am interested in finding this expression of exergy in terms of entropy change of this system. Okay, so I put this as negative because I want you to understand that we are talking about the decrease in entropy of this flow system because of the heat transfer. Okay, that is the reason why I put this as negative. So what you will be getting it as the expression as del Q plus T naught into ds, and this ds is, mind well, this ds is of the closed system. And as I said that this value of ds would be negative. Okay, this value of ds would be negative because why this value of the closed system ds would be negative? The reason is because the heat is rejected by this closed system. Okay, so because this is negative, so obviously the Carnot engine work has to be less than del Q. So this del Q is a heat transfer. So if I want to find the exergy of this closed system associated with del Q, what I do is that I take this value del Q plus T naught into ds, and actually this is negative. So in a way, this is del Q minus T naught delta S. Okay, del Q minus T naught delta S. Okay, so this expression is, let us say, call it as some expression 2. Right? So your expression 1 was what? Look at this expression 1. Expression 1 is what? dW total is equal to del WC plus del WB. Okay. What is this dW total? Is a total work output when there is a small heat transfer del Q and a small expansion dV. Okay. So this is a summation of del WC plus del WB. What is del WC? Del WC, as I have calculated here, del WC is equal to the exergy of del Q and is equal to del Q plus T naught ds. Del Q plus T naught ds, where this ds is the ds of the closed system and its value is always negative when the heat is rejected by the closed system. Okay. Now let us call this as expression 2. Now let me calculate what is the exergy because of the expansion work. Okay, so let us go to the next slide. Okay, I guess that okay, I am writing it here. Del Q of the expansion work is, as I said, the expansion work is the boundary work, right? And by applying the first law of thermodynamics to this closed system, what is the first law of thermodynamics in this closed system? For closed system, first law of thermodynamics is del Q is equal to du plus del W boundary work. Are you getting this? Del Q is equal to du plus del W boundary work. Now, this del Q, if you are talking with reference to the closed system, heat is rejected, so I will take this as negative. I will take this as negative. So what it means is that del WB is equal to minus del Q minus du minus du. Okay, are you getting this? Minus del Q minus du is del WB. But then what we are interested is not del WB, because your expression one we are talking about del WB. So if I want to write this here, so what is del WB useful? Del WB useful is equal to dWB minus P naught dV. But what is dWB? We had already talked about dWB. Del WB is equal to minus del Q minus D. Okay. So this expression, that is, let me choose another pen here. I'm choosing blue. So this expression is what? This expression is the work, boundary work. Okay, boundary work. And I'm not interested in boundary work. I'm interested in the useful boundary work, because that is to be considered when you are talking about exergy. Okay, so this expression I will be substituting in the useful boundary work thing. So what is that? So this expression is, now this expression becomes minus, let me see what it is, minus del Q minus du minus del Q minus du. Okay, this is for the boundary work. This is for the boundary work minus P naught dV minus P naught dV. Okay, let us call this as expression 3. What was your expression 2? I would be borrowing that expression 2 from the next slide. So expression 2 was this. This was the expression 2. Okay, this was the expression 2. Del WC is equal to del Q plus T naught delta S. Del WC is equal to T naught plus. Okay. So the expression 2, I am writing it here. Del WC is equal to, what was that? Del Q plus T naught delta S. Del Q plus T naught ds. Mind well that this ds is not of the engine, but this ds is of the closed system we are talking about. Okay, closed system. So this was your expression 2. This was your expression 2, right? So from 1, 2 and 3, what you get is that you get an expression of del W total. So I'm just rewriting this. Del W total is del Q plus T naught ds, okay, and plus useful boundary work, that is minus del Q minus du minus P naught dV. Okay, this term is the net useful boundary work. So if you look at this gets cancelled off, and you are left with my expression, which is minus du plus T naught ds minus P naught dV. Okay, this is called as, this is called as dW total, del W total. Okay, I hope up to this point it is clear. Any doubt up to this point? Let me ask you. Up to this point it is clear. Yes or no? Whether any doubt regarding this? Gargi is saying she has understood. Others? Okay, Ganesh wants me to repeat this. Anybody else? Okay, taking Ganesh as a representative of the students who want me to repeat. Okay, I am repeating this. What is okay? What somebody Kunal is asking equation 3. Okay, what you want about equation 3, Kunal? Kunal, what do you want about equation 3? Okay, let me repeat this for Kunal, Ganesh, and all those. What is the objective? What we want to find? Let me ask you what we want to find. What is that we want to find? We want to find the exergy of the closed system. What is that we want to find? We are interested in finding the exergy of the closed system. Now, exergy of the closed system is what? Exergy of the internal energy of the closed system. Exergy of the closed system is what? Exergy of the internal energy of the closed system, right? Now, how can the internal energy of the closed system change? The internal energy of the closed system can change either by heat transfer or by work transfer. Are you getting the point? We are interested in finding the exergy of the closed system. Exergy of the closed system means exergy of the internal energy of the closed system, right? Now, how can the internal energy change? The internal energy of the closed system can change by heat transfer or work transfer. Okay. So, if you want to find the exergy of the closed system, you need to find the exergy of the heat transfer from the closed system and the exergy of the work transfer from the closed system. Right? Is this point clear? Is this point clear that if you want to find the exergy of the closed system, you need to find the exergy of the heat which is associated with the closed system, and you need to find the exergy of the work which is associated from the closed system. Okay, so Ganesh is saying that he has understood this point. Okay, now how do you find the exergy of the heat transfer? How do you find the exergy of the heat transfer? Any answer? The exergy of the heat transfer can be found out by doing a thought exercise. What is that thought exercise? That thought exercise is that you need to assume that there is an engine, and that engine is not an ordinary engine, but there is a Carnot engine which is being supplied with this heat. Okay, and this Carnot engine rejects the heat to the surrounding, which is a dead state. So this work output of the Carnot engine, is the exergy of the heat which is being transferred by the closed system if it interacts with the surroundings. Okay, I have taken this direction as outside because I have assumed that the temperature T1 is greater than T0. Okay, so in order to find the exergy associated with the heat transfer, we do a thought exercise that this heat is taken to a Carnot engine, and the Carnot engine rejects the heat at the dead state temperature, and the work output of this Carnot engine is the exergy of the internal energy, is the exergy because of the heat transfer from the closed system. This is the first part, right? Now, as I've said, that it is not simply that there is a heat which is being transferred by the closed system, there is also the work which is being transferred by the closed system. And that work which is transferred by the closed system is not the flow work, it is the boundary work. That is, the boundary would move. The boundary would move. And why would the boundary move? Because of the pressure difference between the system and the surrounding. Okay. However, it is not the PDV work. It is the This is the PDV work minus. That is, it is the displacement work minus the work which is resisted by the atmosphere. Okay. So we need to differentiate between the boundary work and useful boundary work. So the useful boundary work is what? The useful boundary work is the boundary work minus the resistance, the work which is used for overcoming the resistance. Okay, right? So this is what is the useful boundary work. Now, if you want to find, if you want to express this in terms of heat and work, what you do is that you need to express this in using the first law of thermodynamics as applied to the closed system. What is that? The first law as applied to the closed system is dq plus du, okay, minus pdv. So this is nothing but this. Why I put this dw? Because you know that q is equal to delta u plus w. Okay, in this case dq is equal to du plus dw, and this heat is rejected, so I am putting a negative sign, right? So instead of dw, which is boundary work, I put as dwb is equal to minus dq. Sorry, here it would be minus. It would be minus dq minus du, minus dq minus du. Okay, so this is just rub this. Let me erase this. Okay. Okay. So this is minus dq minus du minus p naught dv minus p naught dv. So this is your useful boundary work. Now what we need to do is that we need to add this. We need to add this Carnot work with the boundary work, because I'm talking about a small transfer of heat. So we need to add this Carnot work with the useful boundary work to get the total work, which is the maximum work potential, when a small heat dq is transferred and the expansion is through a small volume dv. Okay, so why we are getting the maximum work potential? Because exergy is nothing but the maximum work potential. Okay, so what we do is that we calculate dw maximum or dw total, which is equal to the Carnot work plus the useful boundary work. Okay, and by putting this, you will get the equation, this equation which I written in the bracket. Okay, hopefully this is clear to you. Ganesh, is this understood now? Ganesh? Ganesh is saying he has understood. Others have understood. Anybody who has not understood this? If you have not understood this, I will repeat this derivation in the next class. Not today, but in the next class. Anybody of you who has not understood this derivation? Kunal, have you understood this? Kunal, equation 3. Okay, Atharva has not followed. Atharva, I will explain this again. For Kunal, it is clear. Atharva, I will explain this again. For Kunal, it is clear. Calculation of exergy of a closed system is calculation of the exergy of the internal energy of the closed system. Now, how can the internal energy of the closed system change? The internal energy of the closed system can change either by work transfer or by heat transfer. Okay, so if I want to calculate the exergy of the heat transfer, what I need to do is that I need to allow that heat to go into the Carnot engine. Okay, and the work output of that Carnot engine is the exergy of the heat transfer, right? How do you calculate the exergy of the work transfer? The work transfer in the closed system is the boundary work, right? But it is not simply the boundary work which has to be calculated if you want to consider the maximum work potential. This boundary work is done this boundary work is done against the resistance offered by the dead state. Okay, that resistance is the resistance P0 dB. Okay, P0 dB. So we need to subtract the P0 dB from the boundary work. So what we get is the useful boundary work. So the useful boundary work plus the Carnot work is the maximum work potential one can extract from the closed system. Okay, that is the maximum work potential one can extract from the closed system, and that maximum work potential is nothing but the available energy or exergy of the closed system. Okay, is this clear, Atharva? See, conceptually you can look at it. The other thing, derivation, you can mug up, and that is not a very great thing. Okay, you can remember the steps. You can just, without understanding also, one can do the derivation. Without understanding any concept, one can do the derivation. So derivation is not a big deal. I want you to understand it conceptually. What are we calculating? Is this clear, Atharva? Okay. So the last step of this, yeah, Atharva, thank you. The last step of this derivation is simply you need to integrate this del W expression between the limits, which is the initial state is 1, to the dead state, which is 0, we can say. Okay, 0. So 1 to 0, if you integrate, you get an expression for the available energy. Okay, so in the next class, I'll just write down that expression, repeat this derivation in brief, and then I hope it would be clear to you. Okay, and then 1 or 2 problems on the exergy of the closed system. So with this, I end this webinar. Thanks for being online. Have a good day.